Welcome to an interesting discussion of accurate mass, quant, performance scalability. So as an intro here, we need to make some assumptions. First, I'll assume that you're involved in target screening, one target ion, and also interested in the match score to build confidence that that is the right target. And I'll also assume that you are analyzing results from one instrument on one shift. So that assumption with an 8-hour shift means that 50 samples is basically more than you could do at 10 minutes elapsed time for the run. So 50 samples is considered the high end of the sample dimension. And we'll talk in a moment about the target compound dimension and move on to the findings. Let's look at the experiments. First, we're going to use a measure of an analyze time, reported in milliseconds, for a compound sample. That means the time it takes to analyze one standalone compound, regardless of the size of the batch. Now we're going to break that into two measurements. The first is the time it takes to do target extraction. That would be straight stick quantitation, just extracting the target ion, that's it. And the other case is the combination of the target extraction with the spectral extraction. So you're going to see the relative performance and the cost of adding in a saturation-aware spectral extraction to complement your target quant results and also provide you with that spectral conformational evidence. While you are absorbing this graph, let me record that these experiments range with target compounds from 100 to 1000. And the data is acquired from a 20-minute LC-TOF run. It's performed on a shipping Z400 with a shipping 8 gigabytes of memory. Yes, more memory can make a difference. So let's look at the graph. A lot of detail, but the first thing to notice is there is a slight compound sample time increase as we move from 10 up to 50 samples. It shows a behavior at the high end, the 1000 compounds, which is often referred to as the performance knee. So you start to see at the 1000 compounds a non-linear behavior where it takes longer as that batch has grown. So for your particular use, you take the number of samples in your batch times the number of compounds in your method and then multiply by the compound sample time and you'll get a ballpark estimate. Mileage may vary. Let's compare the time it takes to not only do target extraction, but we're going to add in the cost of the spectral extraction. So if we go back and forth and first look at just the target, and keep your eyes fixed because the axes don't change, and then we add in spectral extraction, you'll see that it takes longer. So comparing the small and the large batches with respect to the additional time required to handle calculating match scores. On a relative basis, the smaller batches require about double the time. So if we look back, you can see that the time for these smaller batches tends to, let's say, about double. If we compare the large batches, and let's focus on the 1000 compound 50 sample batch, if we look at the time it takes on this end and then adding spectral extraction, you'll only see, let's say, a little bit more than 10%. So the relative cost of that calculation does depend on the batch size. An interesting phenomena is the variation in analyze time that you see by the spread shown by the error bars. So if we look at these lower samples, you can see that the time taken for the second and third time that it's done, there's 3 points for each configuration, is significantly faster than the first time. And the reason for that is there's a caching effect. And that's because the data is held in memory, and the second and third time that you go after it, it's faster to get a hold of it. Now the amount of influence, if we go to the larger size, let's look at the 50 samples in the 1,000, you can see that the caching effect doesn't play as big a role, and that's because the data is much bigger in terms of keeping all that there in memory. Thanks for your attention.